stages and before ocean call his name, chasing fish and fighting in pain. Line cast out to sea, sun above and solid breeze. Hands are worn and tired, heart and mind are still inspired. Row, row against the tide, fear and hope, right by your side. Fight, fight till the end. Old man's courage won't bend. Fish struggle strong, old man sings his lonely song. Battle through the night, moon and stars bring silver light. Eyes like steel, they're sad, never giving up just yet. Marlin was a heart, old man's hands are badly scarred. Row, row against the tide, fear and hope, right by your side. Fight, fight till the end. Old man's courage won't bend.
Hello. Welcome to People's University Marine Biology. I forgot to print out my information, so I'm going to have to look at my phone. I'm sorry about that. So tonight, this is the 6th installment, and as you can see, it's called The Amazing Ocean Realm. And we have one class left after this, and Dr. Smosna and Dr. Bruner will be back next week, and that'll be about coral reefs, which is a really important one. But I hope you've enjoyed the series, and it's good to have someone here in person. Although I thought the Zoom wasn't bad. Right? Okay. Yeah, all right, yeah, okay. We'll do better. Instructors Dick Smosna and Kathy Bruner, am I saying your names correctly? Yes. Husband and wife geologists and teachers have taught for over 30 years at West Virginia University, offering courses on oceanography, marine geology, and marine biology. Since retiring, they have a part-time faculty position at the University College Cork in Ireland. Dick received his PhD degree from the University of Illinois. I'm not going to read what he wrote there. Before joining, he said sometime in the Jurassic period. Before joining WVU, he worked as an environmental geologist with the West Virginia Geological Survey. He now teaches regularly at WVU's Lifelong Learning Institute. Kathy received her PhD from WVU, and she worked for many years as a consulting petroleum geologist for industry and at the U.S. Department of Energy's Research Lab in Morgantown. And so here they are, Richard Smosna and Kathy Bruner.
Okay, we always work as a team, Kathy and I, but I give the talks, all right? She does all the work and I give the talks and I get the applause, and it works out well that way. So, what I want to talk about today is the ocean realm. As soon as I get the electronics working. Okay. Got the mic on, so I'm going to have to stop swearing here. Okay, so here we go. You have to. Yeah. It's on. Isn't it done? You have to point at the screen? Point at the screen.
Just hit the down arrow.
Oh, the down arrow. Okay. Yeah, that's okay. I think we're set now. Okay, so I want to start out by saying that from the very beginning of time, I think people have been afraid of the ocean. Okay, viewing the ocean as foreign or wild or violent. As a matter of fact, psychologists and psychiatrists have a special term for this, which is thalassophobia, which is, you can't read, but it's on the bottom of the screen. Thalassophobia meaning fear of the oceans. Okay. So what I've got here on the first screen, on the left-hand side is a colorized engraving from 1801 showing the Scandinavian kraken. Perhaps you've heard of kraken. It's from their mythology, and kraken was a giant monster, sometimes described as a giant squid, sometimes as a giant octopus, sometimes even as a giant crab with big claws on it. And kraken was as large as a fishing vessel and could come out of the deep ocean and grab the entire fishing boat and entire crew and drag them down to the bottom. Okay. On the right-hand side, we have something a little more recent, but just as fearful, perhaps, and that is a poster from Spielberg's movie, the Jaws, okay, which was based on the novel Jaws by Peter Benchley. Now, Kathy and I have never read the book. Kathy and I have never seen the movie because we're scuba divers, okay, and we just don't want to know. It's just okay. But so what I'm trying to say is that people have always been afraid of the ocean, okay, and I couldn't find a better picture to explain that than the next one here. A typical beach scene along the east coast of the United States, okay? So this is high summer in July, and there's thousands of people on the beach. On the beach, on the sand, okay? And there's a handful of people in the water. And the people in the water are, I guarantee you, they're not in water depth any more than knee deep, okay? You don't go in the ocean. But for the purpose of this talk, I want to emphasize that, in fact, the ocean is a perfect place. It's a great place to live, okay? Maybe not for humans, but it's a great place to live. Because think of this. Life on Earth began 3.5 billion years ago, not much longer after Earth formed, 3.5 billion years ago, and that was in the ocean. And for the next 3 billion years, as life evolved on Earth, it was confined to the ocean, okay? The first amphibian crawling out of the ocean and walking on land was a fairly recent invention, okay? And even today, most life, by far and away, most life in the Earth today is still in the ocean, okay? Life in the ocean is great, okay? It's not to be feared. Oops, I think I had another slide in between. Okay, so here's the gist of our talk, okay? Why is life in the ocean so perfect for marine critters, okay? Because everything you need is in the water around you, okay? Food is everywhere. Essential nutrients, the chemical nutrients that you need for your metabolism is in the water around you, in the very medium that you're swimming through. Buoyancy supports your body. The water temperature is stable year-round, okay? And water pressure is high. That affects humans, particularly scuba divers, okay? But it's no problem for marine animals. So for a whole list of environmental and physiological reasons here, life in the ocean is really good. Okay, so let me just go through that list and kind of explain some of the details. First of all, food is everywhere, okay? You don't have to go out searching for food. You don't have to go out hunting for food in the ocean. You just open your mouth, okay? It's everywhere. This, of course, is a staged picture, okay? But it's showing you the examples of marine life that's the food source for most critters living in the ocean, okay? Now, these are mostly microscopic. A lot of it is algae, but there's some animals in there as well, okay? But food is everywhere, and the ocean is just filled to up their eyeballs in food, in this kind of food here, okay? So the algae that are floating in the water, the base of the food chain in the ocean, okay, is termed phytoplankton. Phyto means from the Greek or from the Polish or something like that. Phyto means plant, and plankton means critters that drift in the water, critters that float in the water. So phytoplankton refers to algae floating in the water, the base of the food chain. Maybe you recognized phytoplankton from food food supplements at your at the local drugstore. Okay, people drink phytoplankton, right? Okay, because you buy it at the drugstore, you get it at Kroger's, and it's good for everything. And here's just one ad, one commercial telling you how good phytoplankton is to consume for humans. Okay, it's the king of the superfoods, right? It helps in cell regeneration, liver health, heart health, brain health, health. It's good for all that ails you. One of the most common algae floating in the water that makes up this group called phytoplankton, where the most abundant algae in the water are dinoflagellates. Okay, and what I have here on the picture left is some dinoflagellates from seawater. Dinoflagellates are unicellular organisms, single-celled animals, single-celled algae, okay? But often they will link together, as you can see here, in long chains, okay? But they're still unicellular, single-celled plants, okay? Dinoflagellates are another common ingredient to the phytoplankton, the base of the food chain. Here's a picture of a couple phytoplankton taken from the ocean water. Phytoplankton are usually classified as microalgae. They're unicellular, microscopic in size, algae, and just like algae anywhere, they'll photosynthesize their own food. Okay, so they take sunlight, carbon dioxide from the water itself, and make carbohydrates, make lipids, make fats, make organic material, make their own food. Strange thing about dinoflagellates, however, is they also consume other critters in the water. They make their own food, so they're photosynthesizing their own food, but they will also eat bacteria. They will also consume other phytoplankton in the water. Very strange. When I was in high school, when I took biology in school, it was really easy. Plants make their own food, animals eat others. Okay, but dinoflagellates do both. Okay, and they have these little flagella, which are like a tail, like a little whip sticking out of their body that allow them to move around a little bit. Okay, but still they're at the whim of waves and tides and ocean. Okay, they're just floating in the water. Where they go in the ocean is wherever the waves and the tides and the currents will carry them. Okay, dinoflagellates, perhaps you know them from something more sinister. Okay, they're responsible for the red tides. Okay, normally in ocean water, dinoflagellates are not very abundant. You go and get a sample of ocean water, a liter or a quart of ocean water. Take it back to the lab and see what's living in the water. You'll see dinoflagellates, and there'll be hundreds of cells of dinoflagellates in 1 liter of water, 1 quart of water. But at certain periods of time, what's called a dinoflagellate bloom or an algal bloom, the population just explodes and goes crazy. Instead of having hundreds of cells of these algae in a liter of water, there'll be millions of cells. Okay? This usually occurs when there's an influx of human pollution into the water. Nutrients into the water will allow the dinoflagellates to bloom. But when they bloom, they're so abundant now, they turn the water red. Okay? People call this a red tide. It has nothing to do with the tides. It's just a bloom from the algae because of the pollutants in the water. Okay? But the problem here is that the dinoflagellates produce a toxin. That's how they get the bacteria that they eat. That's how they get their own food. Okay? They produce a toxin into the water which will stun them. But when there's a dinoflagellate bloom, when there's an algal bloom, there's so many dinoflagellates, so much toxin in the water, you'll have a massive fish kill. Okay, the poisons that they emit will affect the fish and eventually, well, it'll affect their breathing system and they'll suffocate and they'll die. As a matter of fact, people in the water can get harmful effects as well. In the United States, red tides are fairly common, I would say, fairly common on the Gulf side of Florida, okay, on the Gulf of Mexico side of Florida. And when a red tide occurs there, what they do is they just close down the beaches. Okay, get all the people out of the water, get back home because it's actually quite detrimental to people as well. Okay, and these are zooplankton, there are animals that are floating in the water as well. Okay, the algae floating in the water, they're the plankton, but there's also zooplankton. Zoo means animal, zoo means animal, plankton means drifter. These are small critters. They may be microscopic, but most of them are big enough to see with your naked eye. Okay. And they're floating in the water as well. They're part of the food chain, okay? So you got the algae, and you also got the animals floating in the water. And these are called copepods, okay? And the nickname for copepods is insect of the sea. And the idea here is that on land, the most common animal group on land are insects, okay? These are the most common animal group in the ocean. So to be cute, we'll call them insects of the sea, right? Okay, so these are visible with the naked eye, but they're about the size of a sand grain or something like that. Okay. Here's another kind of zooplankton, another animal. Okay, this is called a krill. Okay, it looks like a shrimp. Okay, it's kind of like a cousin to the shrimp, much smaller, of course. Okay, but floating critters in the world's oceans. Okay, so here is a food web. Here's a diagram showing the food web of maybe the North Atlantic Ocean and extending up into the Arctic Ocean. Okay, so in the middle here, circled are the phytoplankton, the algae floating in the water. Okay, this is the base of the marine food chain, and just to the right of that are the zooplankton, which are feeding on the phytoplankton. And then here's my point: all the other critters that live in the ocean, swimming in the ocean, floating in the ocean, on the seafloor, all the other critters in this picture depend on, directly or indirectly, the plankton that's floating in the water. That's their food source, directly or indirectly. But the food is everywhere. Okay, so like I said, you just kind of open your mouth and you've got dinner here. Okay, so all you have to do is just grab it when it goes by. You don't have to hunt. You don't have to go out on a safari to hunt dinner tonight. Okay, the dinner is floating in the water all around you. What you do is just grab it as it goes by. So this is a barnacle. Okay, a close-up of barnacles are really like tiny things. They're about an inch in size, right? Okay, but it's a good example of a animal living in the ocean that's feeding on the plankton. So barnacles, as you probably realize, will produce a biological cement, and they cement themselves to the seafloor. Okay? So once they're cemented on the seafloor, they don't move. Okay? So they can't hunt. Okay? They can't go after their food. They're dependent on the food coming to them. So this barnacle, about an inch tall, really. The pink is its shell. It's actually inside that shell. Okay? Cemented to the seafloor, or cemented to a coral reef, or cemented to the bottom of a boat, whatever, right? Okay. And inside the shell, the animal itself, the barnacle itself, is really upside down. He's standing on his head, okay? And what sticks out of the little hole on the top, okay, are his legs. Those are his legs doing a handstand, okay, sticking his legs out. And the legs are just kind of drifting through the water, just waving through the water, collecting food. Any food that goes drifting by gets caught on those hairy legs, and they'll pull the legs back into the shell, into its mouth, and that's how it feeds. We also have the whale shark, okay, which is the largest fish in the world, right? The whale shark. Despite its name, it's not a whale. Okay, it's a shark, okay, but it's a good shark. It's a nice shark. It's a friendly shark. Okay, it eats plankton. Okay, the largest fish in the world. It's up to 60 feet long. Particularly the males get up to that length, weighing 20 tons. Consumes about 40 or 50 pounds of plankton a day, and this is how it feeds. It's just swimming through the water with its mouth open, and all the plankton that's in the water just kind of pulls into its mouth, and that's dinner. Okay, so the second point that makes the ocean such a good place to live is that the essential nutrients that you need for life are right there in the water. Perhaps the most important chemicals we need, okay, the most important chemicals that any man needs: N, nitrogen, P, phosphorus, Fe is iron, and C is carbon. Those are just four of the most important chemical nutrients that all life on Earth needs, okay? We get our nutrients, our chemical nutrients, from the food we eat, okay? If we don't have enough iron in our body, we've got anemia. If we don't have enough phosphorus, if we don't take enough phosphorus in our body, we get weak bones, okay? The animals in the ocean just take it the water just pours right into their body, right through the pores in their body, okay? And the water in the ocean has all the necessary chemicals for their metabolism. So a lot of these chemicals actually originate on land, okay? The weathering of rocks on land, and then rivers will carry those chemicals, usually in suspension, dissolved in the water, carry that to the ocean, okay? So the nutrients in the ocean originate most likely on land, okay, by erosion carried by rivers. But you also have chemicals from the atmosphere that will dissolve directly into the water, okay, nitrogen and phosphorus and iron, nitrogen and carbon dioxide. But there's also hydrothermal vents on the deep sea floor, which are spewing out hot fluids, hot waters from the Earth's interior, carrying some of these very same chemicals to do, and up into the water. Okay? And then the currents will mix it all together so that everywhere those chemicals are present everywhere. But all you have to do is just take the water in through your body, through your pores, to get all the necessary ingredients. Okay, so here is a chart, okay, showing you the composition, the internal bodily composition of a handful of marine animals. So what we have here are mussels and squids, crab and sea urchin, and all these chemicals over here, sodium, potassium, calcium, magnesium, chlorine, sulfur, all these chemicals are the composition of their bodies, the composition of their internal fluids, okay? Like the composition of your blood, but the composition of the internal fluids of these animals. Okay? And the bottom line is the composition of seawater, average seawater. And you can see that, look, they're all identical, okay? Seawater has 478 sodium, and all these animals have about the same amount of sodium in their body. Okay, here is 10 parts per million of potassium. All these animals have the same value of potassium in their body. You understand what I'm saying is that the chemistry of these animals, okay, matches almost exactly the chemistry of ocean water. Their internal body chemistry is essentially ocean water, okay? So when they take water in from the ocean around them through their pores into their body, it's the same stuff. It's what they need, okay? And so, okay, for example, here, it's a little high. Okay, the top map shows the distribution of just one of these nutrients, just one of these chemicals, phosphorus. Okay, you need it for strong bones, right? Okay, so here's the distribution of phosphorus in the world's ocean. And the red colors here and the orange colors here show you where it's the highest values in the world's ocean. And maybe surprisingly to you, the highest values are in the cold Arctic waters near the North Pole and in the cold Antarctic waters around the South Pole. That's where phosphorus is most abundant in surface waters around the world. And then the bottom map shows the concentration of phytoplankton, algae floating in the water. Where are all the algae most abundant in the water? They're around in the North Pole and around the South Pole in the cold polar waters, okay, where there's most phosphorus. Okay? They're there because that's where the phosphorus is. They're there, that's where the nitrogen is. The phytoplankton are there because of the chemicals, okay? And then the animals are there because of the phytoplankton. Everybody's related. And here's what their skin looks like. Their skin, okay, their outer membrane, okay. It's not much different than your skin too, but skin, okay, what we have here is a double layer of these things that kind of look like, what, kind of toothpicks or something like that. These are fat molecules. The cell membrane of you and me and most animals, the cell membrane is made out of fat, and you can see there are pores going through. And we got chemical nutrients outside the body, and we need chemical nutrients inside the body, and our skin has all these pores through it. So it's really easy for the molecules to move from one side of the skin outside to inside to the body. Okay, so here is a sea slug. A sea slug is not much different than the slugs in your garden. You know what a slug is? A slug basically is a snail without a shell, right? Okay, a snail without a shell. There are land slugs in your garden, okay, but there's sea slugs in the ocean. They're cousins of slugs on land, okay. Oh yeah, I should say, here's how people give common names to marine animals. This is the way you name an animal, a newly discovered animal in the ocean. You look at it and you say, what on land does it most likely look like? What in my backyard does that look like, okay? And somebody will look at that and say, what's a slug, okay? So then you put the word sea in front of it, which makes all the difference in the world. So sea slug, okay? But what I'm saying is that the water outside the sea slug is exactly what the chemistry of the body is, and it just moves through its skin, through the pores inside. Meanwhile, water is moving out. It's a two-way street, okay? Water is moving in and out, and in and out, and in and out through the pores of the body. Okay, a third factor that makes life in the ocean so interesting, so enjoyable, so happy is you got buoyancy to hold up your body, okay? Me standing up here, 6'2", I need a skeleton okay, to hold up my body against gravity, okay? If I did not have a skeleton to support my body, Dick Smosna would be a little puddle of protoplasm on the floor right here, okay? My skeleton holds up my body against gravity. But in the ocean, you got buoyancy to support the animal, and you don't really need a skeleton at all, as a matter of fact, okay? So here's a little physics for you. Okay, here's what buoyancy is. The force of buoyancy is this. Okay, it's an upward force. Okay, and it's simply the volume of water displaced. Okay, so in the beaker over here, we got an object floating in the water. Okay, and the bottom part of that object, the bottom half of the object, is pushing the water aside, right, as it's sitting down in the water. So the volume of water that's pushed aside by the object, by your body or my body, the volume of water displaced times the density of the water times the force of gravity, those three numbers multiplied together is the force of buoyancy, okay, which is pushing upwards on whatever's in the water. So now, as an example here, okay, so the force down on your body when you're swimming in the water, okay, is basically your weight, right? Okay, and your weight is related to how dense your body is. Okay. The weight of your body is related directly to how dense your body is, okay? Adults are about 60, all of us here, our body is about 60% water, okay? So the density of my body is about, on average, what we've got, 1.096 grams per cc, okay? Water has a density, pure water has a density of 1, so my body is just a little bit denser than water. Okay, 1.096 grams per cc. Then the force of buoyancy lifting up on my body or lifting up on anything floating in the water, the force upward, buoyancy, depends on the density of the ocean water. And density of ocean water is 1.020 grams per cc. So you see the two numbers are quite similar, are quite close together. So what I'm saying is that humans made up 60% of the water. My body is just a little bit denser than water itself. So the buoyancy force here pushing up on my body is almost equal to the gravity of my weight pulling down. Okay. But now marine critters are usually much more have much higher percentages of water in their body. Angelfish here, the beautiful angelfish, 72% body weight water. A jellyfish, 96% water. So you understand where I'm going here, that their body is as dense, has the same density, almost the same density as water itself, okay? The buoyancy will hold, buoyancy equals their weight. The buoyancy up equals their weight down. They don't need a skeleton to hold themselves up. The buoyancy is doing the entire job. Okay, so here, okay, so you don't need a heavy, you don't have to put a lot of physiological processes or effort into building a skeleton. You can forget that completely, okay? Because the buoyancy does all the work, essentially does all the work. That's why so many critters in the ocean look so weird to our eyes, okay? So that's why we get strange, delicate shapes, soft, gelatinous bodies. So we get something like a jellyfish floating in the water. You'd never see anything like that on land, okay? It couldn't survive because it doesn't have any skeleton. Or a sea slug on the right, or a tunicate on the left. Really strange bodies that look otherworldly, okay? Simply because buoyancy holds up their body and they don't need to be, they don't need a skeleton. Here, sperm whales, male sperm whale weighs up to 50 tons, okay? Females are considerably smaller. But it's 50 tons here. And everybody knows what happens to a whale when they beach themselves, okay? Like in the bottom picture here, they're killing themselves. They die, okay? Because their weight out of the water where there is no buoyancy, their weight will crush their internal organs. I mean, there's other reasons why they might die from exposure as well. But the prime reason is that their body is no longer supported by buoyancy, and their own weight, 50 tons, will crush their own internal organs, and they'll die on the beach. Okay, now the water, another great thing about living in the ocean is that the water is always the same temperature. The water never changes temperature. Now, it varies across the ocean, okay? But at any one point over the course of the year, it stays the same, more or less, year-round, okay? So here is a map of the world's ocean, okay? Ocean temperature. So you see that the coldest waters are the dark blue, which, as you know, are going to be up near the Arctic Ocean, okay, near the North Pole and down to the South Pole. And then the water temperature at the equator, these numbers here are actually in centigrade, but the water temperature in the equator is typically in the upper 80s, okay? So the water temperature in the ocean varies from slightly below freezing near the poles, 28 degrees, something like that, to a high of about 86 at the equator, okay? But, okay. All right, here's life on land, life for you, life for me. This is, so the picture here, the two pictures here are of Morgantown, and there's Morgantown in the wintertime and Morgantown in the summertime, and I'm sure it's not any different than Wheeling in the different seasons, okay? And the graph on the right shows the daily temperature over the course of 1 year from January 1st to December 31st. So the year here is 2023. So the red background, okay, the reddish pinkish background is average high temperature in Morgantown. The blue bottom here is average low temperature in Morgantown over the course of the year. And then the green band here is the average mean temperature in Morgantown. But what's important, what I want to really show you is the dark blue line here. That's the daily temperature. Every day of the year in 2023 is plotted on this graph, okay? And you can see how variable it is, all right? We live in Preston County, outside of Morgantown. And last week, again, probably not much different than Wheeling. Last week, the high temperature was in the 20s. 3 days later, the high temperature was in the 80s. That's in Morgantown in less than 1 week, okay? So what I'm saying is the range in Morgantown, the temperature range in Morgantown can vary as much as 40 degrees in 1 day, okay? And over the course of the year, the temperature from the coldest time, in Morgantown, we get, there's probably maybe 1 day a year where the temperature will approach 100 degrees. On the other side, in the wintertime, maybe 1 or 2 days in Morgantown where the temperature is 0. So I'm saying the extent, the range over 1 year is 100 degrees. So if you live in Morgantown, if you're an animal living in Morgantown, you have to be able to tolerate a 40-degree change in 1 day. Your body has to be able to tolerate a 100-degree temperature change over the course of 1 year. If you can't do that, you're dead, right? Or you move somewhere else. Okay? Temperatures on land fluctuate extreme. Land animals have ways to handle this kind of stuff. One way to handle the winter cold is you shiver, which will make your body a little bit warmer, okay? Or what we'll do is shut off the blood supply to our skin when it's really cold, okay, to conserve body heat. Or in the summertime, we use air conditioning, but we have ways to deal with these extreme temperature changes. Okay. Here is, okay, so Kathy and I are scuba divers, and our favorite place to dive is Bonaire, okay, off in the Caribbean, off the coast of Venezuela. Here is the picture of beautiful Bonaire, and here's the temperature for the water in Bonaire over the course of a year, okay? And again, these numbers are in centigrade, okay? But the hottest temperature of the water in July is 86. The coldest temperature, water temperature in Bonaire in January is 79, okay? It never changes. It's always around 80 degrees, okay? Which means that if you're an animal living in the ocean off the shore of Bonaire, okay, you don't have to worry about temperature. You don't have to put a lot of thought and effort to keeping your body warm in the wintertime or keeping your body cold in the summertime because it never changes. So you don't okay, the biological term for this would be thermal regulation. Your body is regulating your heat, okay? But they don't have marine critters don't have any way of regulating their own body heat internally because it's not needed, okay? Now that what they can do is they can be a little bit more active and that will warm up their body. The heat's given off by their muscles will heat them up to some degree. Or if they can go up higher in the water column to be warmer. They can go swim down a little bit deeper, but that's just fine tuning. That's really minor. They don't have any regulations, any major regulations to govern their body temperature. And the last thing I want to mention is the water pressure. Okay, I hope you appreciate that water is heavy. Water is it's a very heavy liquid. Okay, so right now we're at the surface. We're at the surface of the Earth. Okay, and we have in this room, anywhere you walk on Earth, we have, about 60 miles of air directly above us, right? That's the atmosphere, okay? The atmosphere is approximately 60 miles thick, okay? Now, air doesn't weigh very much, but it does weigh something. And when you got 60 miles of air, that becomes a considerable weight, okay? So the air above us right now, okay, is pushing down on every square inch of your body, every square inch of my body, with a force of about 15 pounds. The air above us, 60 miles of air, is pushing down on every square inch of my body with a force of about 15 pounds, okay? And we call that, the higher math gets too involved, so we just call that 1 atmosphere. The weight of 1 atmosphere, 15 pounds on every square inch, okay? So at the surface of the ocean, the pressure on you swimming or any animal in the ocean right at the surface is 1 atmosphere, 60 miles of air above you. But when you go deeper and deeper and deeper in the ocean into the ocean water itself is so much heavier that if you go down into the ocean 10 meters, if you dive down in the ocean 10 meters, which is just 30 feet, okay, the pressure on your body at that point now will be 2 atmospheres. 1 for the weight of the air above us, and then 1 for that 30 feet of water, okay? So the pressure on my body, if I'm down 30 feet, the pressure on my body is 2 atmospheres. 1 atmosphere of air and 30 feet of water. And every 30 feet, you go down deeper and deeper and deeper, the weight on your body, the pressure on your body becomes another atmosphere. So by the time you're down, so 30, okay, down here it's 4 atmospheres, another 30 feet, 5 atmospheres down to 60 feet, and that water is really heavy. And the atmosphere really, the weight on your body really builds up quickly, okay? And what that does to your body can cause considerable pain, particularly if there's any air pockets in your body. And there are air pockets in your body, okay? So one problem that divers have going down deep, but it's not even deep, it's like 10, 20, 30 feet. Going down 10, 20, 30 feet, the pressure of the water on their body will cause severe pain in their ear because your inner ear is air. It's air-filled, okay? The pressure of the water will push your eardrum in till it's actually painful, okay? Or sinus pain. You have the sinuses in your head. Those are all air-filled cavities. So as you go down 10, 20, 30, 40 feet, the water pressure around you is pushing in on your sinus cavities here, causing you really extreme pain, okay? Or mask squeeze. You gotta, even when you're snorkeling, you got a face mask in front of you, and it's air between the face mask and your eyeballs, okay? And people will go down, and the air pressure will push on their mask so hard, okay? They'll come up and they'll have a red ring around their face, an impression of the mask on their face, and it can hurt, okay? And the extreme is on your lungs. Any air-filled pocket in your body, your inner ear, your sinuses, or your lungs. So here are you swimming at the surface, and your lungs are 100% filled with air, okay? And you go down 33 feet, okay? And the pressure on your body is now enough to squeeze your lungs into half their volume, okay? The atmospheric pressure is now enough to squeeze your lung squeeze is what it's called, cleverly enough, okay? And you go down another 33 feet to 66 feet. Now the water pressure on your body has squeezed your lungs to about a third of its volume, okay? And the deeper you go, the smaller and smaller your lungs become. They're squeezed into a smaller space by the pressure of the water around your body, okay? Now, your lungs are fairly plastic, fairly elastic, okay? And that usually doesn't do much damage. It doesn't really do much damage to your lungs itself. Okay? They're squeezed into a small volume, but when you come back up to the surface, on the right-hand side, your lungs will start to expand as the pressure is reduced. And you get back up to the surface here, and your lungs have expanded to their original size, and all is fair and well. Okay? Okay. I've got a cousin who is an oceanographer, got his PhD at Columbia several years ago. And what they would do for his research, for his PhD research, is they'd get on the research ship, go out in the middle of the Atlantic Ocean, and throw cables overboard. Okay? They never went into the water themselves. Oceanographers don't go into the ocean. Okay? They send tools down into the ocean to do their job. So they would lower a cable over the side of the ship, okay? And the cable was just loaded with instruments to measure the water temperature, to measure the water current, to measure the water salinity, and they had great big collecting grab bags at the bottom to collect samples of the water at depth, to collect samples of the sediment on the ocean floor. Okay, so they'd put all this stuff at the end of a long cable, and then send cable, thousands of feet of cable down to the bottom. And when it made all the measurements, and when all was said and done, when they got all the samples they wanted, they'd reel it back up. But this whole operation of sending it down thousands of feet to 7,500 feet or even deeper, okay, collecting samples and then bringing the cable back up, that would take a good part of a day, right? They didn't have anything to do while they're collecting samples. So just to keep their sanity, what they would do is they would tie their styrofoam coffee cups to the cable along with all these instruments, okay? And as the cable was lowered down, the water pressure would squeeze the styrofoam coffee cup, smaller and smaller and smaller. Now, one thing you have to understand about water pressure is when the coffee cups were squeezed by the high water pressure, it's not like the coffee cup is on the floor and I and squash it flat. That's not what happened. The pressure comes in from all sides, from the top, from the bottom, from the right, from the left, from front and back, squeezing all. So the coffee cup just gets smaller and smaller. It's not flattened. It just gets smaller and smaller and smaller and smaller. Now, when you bring it back up, it's not like your lung. It won't expand back to its original size. It stays at that size, the size, which is like the size of a thimble. Okay? So what they do is they put their names on the coffee cup so everybody can identify it. So they got a souvenir at the end, okay? And then they send it down to 100 meters, 300 feet, send it down to 1,200 meters, send it down to 7,500 feet, and by that time it's squeezed to the size of a thimble, okay? So water pressure is high. Water pressure on anything that's collapsible, okay, can be significant. Humans need protection from this high water pressure. So you don't go underwater unless you have some way to protect your body against lung squeeze and pressures like this. But that's only if you have air-filled cavities in your body, your inner ear, your lungs, the sinuses, okay? Ocean animals don't have any air-filled. They don't have any air-filled cavities, okay? So they don't suffer in any way that I'm describing, okay? So here we have on the ocean floor, 6,000 feet down, and there's all sorts of critters, octopus and crabs and different kinds of other animals here. Here's the internal anatomy of a clam, okay? And I include this here just to see that there's no lungs, okay? There's no sinuses. There's no eardrums in these marine animals. They don't have anything that's collapsible. They don't have any air-filled passage. Any passage in any organ in their body is water-filled. Water is not compressible. Air, yes. Water, no. Okay? So it's not a problem for them. Water pressure is not a problem for them. So here's a sea cucumber. I'm not sure what he's doing standing up to, okay? But they don't have lungs, okay? And here's the internal biology of a sea cucumber. The cloaca at the very end here is its butthole, okay? And these purple things coming out here are its respiratory trees, okay? They're kind of like gills, okay? This is kind of sickening here, but sea cucumbers breathe in this fashion. They take water into their butt, okay? And then the water goes into these respiratory trees, and the respiratory trees act like gills in fish, similarly to gills in fish, take oxygen out of the water for a body for their metabolism, and the waste product, carbon dioxide, is put back into the respiratory trees to go back out in the ocean, okay? But that's all water-filled, okay? So there's no lungs, and there's no water pressure problem. Okay, and fish, let me see here. But it has, because it's an organ that's filled with air, okay, has nothing to do with breathing. It's not a lung. It's not, okay. Fish breathe with their gills, right? Okay. But they do have this other organ inside their body called a, okay, and the swim bladder fills up with gases, primarily oxygen and carbon dioxide, from their bloodstream. So the fish can divert gases from their bloodstream into the swim bladder, and the swim bladder will expand. And when the swim bladder expands, that makes their body less dense, and they'll rise towards the surface. On the other hand, they got muscles around the swim bladder, and when the muscles contract on the swim bladder and squeeze, they'll squeeze the gases out of the swim bladder back into their bloodstream and out into the water. The body will become heavier, denser, and they'll sink down to the bottom. Okay? So they could use this mechanism to move up and down in the water column, okay? And they don't have to exert any swimming, they don't use any muscles at all, okay? I mean, it's a very convenient way to move up and down in the water column with no effort whatsoever, okay? But it is air-filled, and it would be subject to high water pressure if they didn't have a gas gland, okay? So there's another organ here in the bottom of the swim bladder, okay, called the gas gland. And it will put gases into the bladder, okay, to compensate for the water pressure around them. So even though the water pressure around them is getting higher and higher and the pressure is pushing on the bottom, the gas bladder is pushing out with an equal force so that there's no pain, there's no disruption, there's no explosion of their gas bladder. Oh, here. Not all fish have swim bladders, okay? Sharks do not have swim bladders, okay? But they have, their liver is filled with oil, right? I'm not sure about you. When I was a kid, okay, anytime I got sick at all, my mother would get out a bottle of cod liver oil, okay, taken from a cod, but it's not any different than the shark liver oil, okay, here. But that's really a light oil, okay? So they fill their liver with a very light oil, shark liver oil, or cod liver oil to keep their buoyancy up, okay? And here's a starfish, of course, a sea star, okay? And surprisingly, the arms on a starfish are not used primarily for locomotion, okay? You would guess that's how they move across on the ocean floor, okay? But really, the starfish's arms are used for grabbing onto its food, onto its prey, okay? The way it moves across the ocean floor, walks across the ocean floor, is by these tube feet, which are sticking out here on the underside of each arm. So here's one arm of the starfish, and you got all these tubes out here, and they are like they're like suction cups, okay? And here's how the starfish operates, okay? They got a hole in the top of the animal here where water comes into their body. So it doesn't really stand out here, but there's a hole right here, and they can pull ocean water into their body. And when the water comes, it goes through all these little canals into all the arms. So the water comes in through the hole on top, okay, and into this canal system, which leads out into all 5 arms, okay, and it can increase the water pressure, and then these tube feet here are connected to the canals. So when the water goes through the canals, it pushes the tube feet out down onto the bottom, okay? It's like your hydraulic brakes in the car, okay? Your brakes on the car will expand inside the back wheel, okay, because of the fluid pressure pushing them out. Okay? So then it uses these tube feet to move across on the ocean floor. And when it's done, when it's done going somewhere and it needs a rest, it will take the suction cups up, okay, and the water will come back out through the hole in the top, back out into the ocean, okay? But the point is that there's, as great a system it is, there's no air-filled passageways in here. It's all water-filled. Water's not compressible. Water doesn't squeeze. Water is not affected by the high pressure of the ocean. Okay. And then you have blobfish. Okay. This kind of example. Gelatinous, watery fish. There's nothing on this fish that's subject to water pressure. Okay? It's all water-filled and solid material. Nothing air-filled, nothing that's going to cause any problems like to a scuba diver. Okay, so now, oceanographers generally divide the ocean realm into 3 zones based on light intensity. I mean, there's a million ways you can divide up the ocean into different provinces, but one of the most important ways is by light intensity. So we're going to call the surface water, okay, that is lit by the sun, okay, cleverly, the sunlight zone, okay, and that's where most living things in the ocean hang out, in the light zone, okay. As you realize, okay, when the sunlight hits the ocean surface and penetrates down into the water molecules themselves will start absorbing the light. Any mud, any particle, anything floating in the water will also absorb the light as the light is penetrating down deeper and deeper into the water column. So what I'm saying is that the water will decrease, it will get darker and darker as you go down because the water is absorbing the light and anything floating in the water will absorb the light. The deeper you go, there's less and less light. So by the time you get down to about, maybe 600 feet or so, at the bottom of the sunlight zone, there's still a little bit of light left, okay, but not enough for photosynthesis. So where do all the plants live? Where do all the algae live? They live in the upper water where there's light for photosynthesis. There might be a little bit light down, so if you went down below 600 feet, you could probably still see things with your human eye, okay, but there's not enough light down there for photosynthesis, so no algae. No. So that means there's no food. There's no base of the food chain down there. And the midnight zone here is at a depth of about 3,000 feet, and there's no sunlight that will penetrate that deep. I mean, it is midnight. It is like standing inside a closet, okay? So the upper sunlight zone is where 90% of all life in the ocean lives, because that's where the food is. That's where the algae live, okay? As you go deeper and deeper and deeper, you got more and more problems. It's a great place to live if you live in the sunlight zone. Water has got everything you need around you, okay? But if you live in the midnight zone, things are kind of rough, right? So here are the problems living in the midnight zone. Okay? There's no light, okay? So you got to bring your own light if you want to see. So you need really good eyes, okay? So there's so little light down there that you need really good eyes, usually really big eyes, okay? There's not much to eat, right? Okay? Because the base of the food chain is the algae, and the algae are nowhere near, the algae are way the hell up there. So you require special adaptations to gather food if you live permanently in the midnight zone. It's difficult to find a mate. It's difficult to find anything when there's no light. Right? Oops. And the temperature is really cold. The temperature never changes, but it's just a few degrees above zero, just a few degrees above freezing, okay? So that means your metabolism slows down, your activity slows down, all your body functions slow down, and a lot of critters living down here need antifreeze or some kind of insulation to stay warm. Okay, so here is a typical example of a deep water midnight zone, okay? Here's what they look, they're colorless, okay? They're just blobs, okay? There's no light for color. There are no colors down there, okay? So there's no reason for the fish to exert anything biologically to make colors. So they're dark brown, they're black, they're blah, okay? Nothing gaudy, nothing bright, just plain old black, brown, or dark red. And here's what most wood fish, so if you put on your snorkel and went down 3,000 feet and looked around at the fish swimming around you, you'd probably miss them because they blend in beautifully with their non-existent background. You have to bring your own light, okay? So here is some kind of submersible. Researchers are down at the bottom examining whatever critters are living down there, but in order to see what you're doing, in order to see them, you've got to bring your own light. Or if you live down there, you got to bring your own light. Okay, so many animals who live down in the midnight zone, okay, do in fact bring their own light. Okay, and this is called bioluminescence. Okay, luminescence meaning light. Bio means the critters themselves. The critters are making their own light. They're bringing their own light with them. Okay, so here's a star. Here's a quiz. Okay, what animal is that? Okay, so here's a starfish. A deep water starfish that's bioluminescent, okay? It's got cells in its body that produce light, or it's got bacteria living on its body that produce light for them, okay? But deep sea animals can't, not all animals do this, but deep sea animals can create their own light. And what they're doing is not much other than they got the glow sticks in their body. Okay, you've all played with glow sticks when you were a kid. Glow sticks, you buy them at Walmart. No? Okay. Yeah, when you're kids. Okay, but glow sticks have two chemicals inside, one in either end. Okay, and when you break the glow stick in half, the two chemicals can mix together, and a chemical reaction between those two will produce light. okay? And whatever chemicals different chemicals in the glow stick will produce different lights, different colors, okay? But that's essentially what's happening. The same thing for either the animals themselves or the bacteria in their body will produce their light by chemical reactions, okay? And they can actually use different colors, change colors, okay, and give off light. So here's what so some animals use bioluminescence simply to identify their own species, okay? If they didn't have their own light, everything would be pitch black. You couldn't see anything, okay? So if you want to find a mate, okay, you got to advertise. You got to advertise with neon lights, okay? So one use of bioluminescence is simply for species identification. You want to know who you're talking to. You want to make sure that they're same species that you are. Or you can use the bioluminescence as camouflage to blend your body into the background. Okay, so this is a lanternfish. And the upper left-hand picture is what if you caught a lanternfish and brought it up to the boat, that's what you'd see. Okay, that's what it looks like in air. Okay, but at depth, at a couple thousand feet, okay, it's using its bioluminescence along the length of its body, okay, to blend in with the darkness around it. Okay, so you can see that it's becoming invisible. I hope you can see that, becoming invisible. Or to confuse their predators. If you saw something like this, and those lights are flashing on and off and on and off and on and off, okay, that might be enough to put you off or confuse you. Or what some animals will do with their bioluminescence, it's like this. If you were in a dark room with no light whatsoever, and then you turn the light bulb on and turn it off again real quickly, just light on and off, okay? I hope you know what I'm talking about. You would see that image of that light on your retina for a couple seconds after the light went off. You with me? Okay. Okay. So that's your homework assignment. Go home tonight, sit in the closet, close the door, and turn the light on. Okay. No, but that image of light will be on your retina for a couple seconds. Okay. So what you do is you blind your predator with these lights. Okay, and then you turn them off. Okay, and when he's sitting there dancing, you make your getaway. It's a very convenient thing. Okay. Or, okay, you have really large eyes, just to take in as much light as possible from the environment to see what little there is to see. So many of these deep sea fishes have incredibly large, the animals themselves, the fish themselves are often quite small, but it's almost like their eyes are like half their body, okay? So here is a hatchet fish with these huge, huge eyes. Now these fish are small, they're less than a foot long, but their eyes are remarkable, okay? Or a grenadier fish. I'm sorry that it's off the wall, but here's a squid over on the right-hand side with huge eyes, and another fish that you can't see at the bottom. Really big eyes. Okay, so in the upper left-hand picture is the sunlit zone, where there's plenty of sun, okay, and animals are all gaudy colors. You know what coral fish look like, okay? They're really, really gaudy, okay? But in the deep sea ocean, and there's plenty of fish, there's plenty of food up there, okay? But in deep sea ocean, like on the right, there's not much to eat, okay? So what do? Well, you eat each other, okay? That's one possibility. So here are two deep sea fish, one chasing one another. Oh, here's another thing. This is primarily for, deep sea critters, okay? Deep sea animals, particularly small animals here, will, during the daylight hour, this is a graph, basically, okay? So what we have here is depth in the water, from the surface all the way down, okay, into the midnight zone. And going off to the right is time. So here's daylight, okay, here's like midnight, and now these are the night hours, okay? So it's one scene down to great depths, but over 24 hours to the right, okay? So what's happening is during the daylight hours, many of the sea animals will go down to really deep depths where it's dark to escape predation, to hide from their predators, okay? Now they're eating guys up here, but they're not eating now. Okay? Now they're hiding. Now they go down a couple thousand feet where it's dark and they're escaping their predation, okay? But during the nighttime hours, they'll come back up to the surface here when everything is dark and feed, okay? The next day they'll go down and hide in the bottom. Okay, so you see what they're migrating up and down in the water column, hundreds or thousands of feet. Okay, and these are little tiny guys like this. It's often been carried to like the equivalent of going 50 miles to a McDonald's, okay? I mean, they're traveling long distances compared to their small body size, okay, to come up and down the water column, to hide during the daylight hours or to feed during the nighttime. So here's what they're doing, okay? Here are the copepods, the microscopic animals, okay? And here is another picture. This is water depth. This is actually a sonar picture with sound waves into the water. So here we have water depth from the surface down into the midnight zone. And then to the right is time. So this is during the daytime, and it's getting later and later in the day, okay? And now this is nighttime hours, okay? So it's a little bit different, okay? So what you see here during the daytime, all the zooplankton is so thick, so dense at depth, okay, that sound waves will bounce off of it like it's a submarine. Sound waves will bounce off it like it's a ship, like it's a boat. They're so concentrated, so many, okay? And that's what's happening. So what we're seeing here, all these little white dots are the individual animals that are living down there, hiding from their prey at depth, okay? But it's so thick, okay, that sound waves are bouncing off, and you can see it on a sonar screen. And what you see here is that as the daylight gets older and older, okay, later and later, the whole phytoplankton body is moving up into the water column, and in the midnight hours, they're right at the surface, feeding on the algae. And what they'll do the next day is they'll go back down to those depths at all. But they're so abundant, you can actually photograph them. You can actually take a picture of them on sonar. Okay. A really good feast, like the Thanksgiving feast, is when a whale dies, okay, up at the surface, okay, and sinks down to the bottom. I mean, that is a huge feast, one big blob of food, okay, and it's traveling on its way down to the bottom. A deep sea feast. And here is maybe that same whale. This is the bones of the whale on the deep sea floor, okay, the rib bones and stuff like that. And here is a giant crab feasting on that dead whale, okay? Best meal he's had for months, I'm sure. So most of the predators that live down here, okay, have really large teeth. Now remember, food is at a premium here, okay? Really large teeth, really large mouths, okay, and jaws that are highly expandable, okay. Their jaws can actually, the upper and lower jaws can actually separate some of these fish so they can get really big pieces of food into their mouth, okay. And what they usually swallow it whole, predators, okay. They're not like a lion that goes out and takes a bite out of a zebra and takes another bite out of the zebra and just eats it. Okay, they get the whole fish in their mouth, okay, all at once. The mouth is large, and the mouth will expand. The jaws will expand so they can get the entire thing. So here's just some examples of the teeth, the large mouth, and the expandable jaws of these deep sea fish. And then, yeah, okay, so the teeth are so large, okay, they don't even fit in the animal's mouth, okay. They're big enough to grab onto a prey, but they're too big for the mouth, okay. And the jaws will simply snap close over their food, okay. And then here's the anglerfish, okay. This combines two of the best ingredients, okay. They got really big teeth, really large mouth, expandable mouth, and they got bioluminescence on the end of a fishing pole sticking on top of the head. They're using that's a lure, okay, to attract other fish, to attract their prey, okay. So the prey animal will come over here. All it sees is this lure, this bioluminescence lit lure, okay, and it comes over here and says, what's going on out there? And by that time, the anglerfish has got it in its mouth, okay. So it's using the bioluminescence as a lure to attract its prey. And here is the wolf trap anglerfish, which takes everything one step greater. It carries its lure inside its mouth. Okay? So by the time you get to the lure, okay, it's already too late. By the time you snoop it around the lure, you're already inside the anglerfish's mouth. And then we're all familiar with Nemo and Dory and the anglerfish. That's what was going on here. And then, okay, just to go the extremes, okay, here's a jellyfish, doesn't have eyes, okay, of course, okay. But what it has is a really long tentacle, okay? Can reach out way out past its body, okay, to grab food. Food is at a premium, so whatever you have to get more food is better, okay? And if you can reach out way beyond your body size itself, okay? So here's a bell. The jellyfish is only 8 inches across, but its one tentacle is 4 feet long. So it can grab any food within 4 feet of its body, okay? And here's my favorite, the black swallower. Big mouth, expandable jaws, large teeth, but its stomach is expandable, okay? So its stomach can hold a fish bigger than its own body. And what you can see inside there is a fish inside there. He's digesting the fish inside. So the stomach is very elastic. It just expands to hold fish twice as big as the swallower itself. One last problem, or one other problem of deep sea fish is in the darkness to find a mate. Okay, if you don't have bioluminescence to advertise who you are, how do you find a mate when you can't see anything? Well, a number of fish have taken to what's called sexual parasites. So here is a deep sea anglerfish. That's the female. Females are huge, relatively speaking. The male is this guy here. That's an adult male. Okay, so what the adult male will do is attach onto the female. So you don't go looking for sex. You don't go from bar to bar to bar looking to pick up women, okay? You latch onto them, and then you just ride with them for the rest of their life, okay? They'll sink their teeth into the female and hold on, or in some cases, they'll actually blend their body tissue with the tissue of the female, so they're biologically joined, either holding on for dear life with teeth or biologically joined, okay? So the problem of sexual parasitism. And one, I think I got another example here. Yeah, okay, this one here is, so the female is the large one, and here's the male. And this one's actually bonded to tissue, so they're congenitally joined, okay? And some of the species, the males will not reach sexual maturity until they bite onto the female. There's some kind of release of enzymes in their body that will produce sexual maturity, okay? But only after they bite the female. So when they're hunting around from bar to bar to bar looking for females, okay, they're not wasting bodily energy. And then metabolism slows down because the cold water, it's cold water here, okay? So the metabolism slows way, way down, okay? Which allows the animal to slowly grow to immense sizes. Okay? So here is just a deep sea fish, which is probably about 12 feet long, something like that. Here's the, if you've ever been over to the eastern shore eating blue crab, this is what you eat at a restaurant. This is a normal crab. This is a standard sized crab. This is a Japanese deep sea crab. Crabs, all animals, all these animals grow to immense sizes in the deep water. Metabolism slows down, but they live forever. And they grow and they can keep growing throughout their entire life. Humans, we stop growing. Humans stop growing at what, age 20 or something like that, okay? These animals will continue growing throughout their entire life. Because they live forever, they grow to huge sizes. Okay, the giant Pacific octopus, bigger than the diver. Okay? Now, when you go down to the Bonaire or anywhere in the Caribbean and you see octopus in the water, they're the size of your fist, right? Okay? These guys are much, much bigger. And again, the water temperature is cold. Okay? At the bottom of the ocean, the water temperature is usually just a couple degrees above freezing, 40 degrees, something like that. Okay? Sperm whales can dive down to 3,000 feet, from the surface down to 3,000 feet. Okay? Sperm whales are known, they dive down really deep because their favorite food are the giant squids. And the giant squids live down there. So if they want to eat a squid, they got to go down there themselves. They hold their breath at the surface. Right? Whales are air breathers, right? So they hold their breath at the surface. What they do at the surface is they blow the air out of the air hole on top, okay, and then take in air. And how long does that take? It takes like about a second. Blow all the air, all the water and all the air out when they exhale. Then they inhale and and that's enough air to get them down to 3,000 feet for an hour or so. Do you remember when you were a kid and you were at the town swimming pool and you were going to set the record? Me and my buddy were there. I'm going to stay underwater in the town swimming pool and break the world's record, whatever that is. Okay? So what you would do is you're getting ready, right? Okay, to the point where you actually hyperventilate before you pass out. Okay, and then you finally go down underwater, and you're underwater, and you're holding your breath, and you're stomping, and you're gritting your teeth, and you can't hold your breath any longer. And you come up and you say, "How long was that?" And he says, "20 seconds." Oh God! These whales can breathe once in a second and have enough air to last them an hour underwater at 3,000 feet. But what they're after is these guys here, the giant squid. So here's a giant squid that had washed up on shore, and all the tourists are around taking pictures. And here's a sperm whale, and you can't really see it on this picture here, but here's a blow of its skin, and all these circular marks here are sucker marks from the squid. Obviously, they had some kind of big fight underwater before one lost and one won. I assume the sperm whale won. And here's a typical depiction, Walt Disney depiction of the sperm whale fighting the giant squid. But to handle the cold temperature, 40 degrees year round, they got a lot of blubber, right? So immediately under the skin for the sperm whale here, that is its blubber. It's sometimes up to a foot thick, which is just fat, okay? It's just fat under the skin. You've got a little bit of fat under your skin, okay? It doesn't do you much good in the ocean, okay? But yeah, so they got 6 inches to up to a foot. And some deep sea fish actually have what you might call antifreeze in their bloodstream. It's a chemical, it's a protein in their bloodstream, okay, that will prevent ice crystals from growing in their bloodstream, okay? So when they're down there at depth and the water temperature is near freezing, okay, ice crystals will actually start forming in their bloodstream, which is bad, okay? But they got chemical proteins in their body which will... In this picture here, it's kind of a sketch, okay? The white is ice crystals growing in their bloodstream. And this stick figure here are the proteins that their body produces, which will latch onto the ice crystals and deform the ice crystals and prevent them from growing. So essentially, it is keeping their bloodstream ice-free. Even though the temperature is cold enough to make ice in the bloodstream, they can prevent the ice from forming. Oh, and listen, one last comment here is that as horrible as the deep sea environment is, okay, as disadvantaging, okay, you have to remember that some people think that the origin of life on Earth 3.5 billion years ago was down in the deep sea midnight zone. There are deep sea vents on the floor which are tapping into the Earth's interior. And what you see here are gases, really hot gases and liquids coming out that are just laden with all sorts of minerals that are necessary for all living things. So one idea about the origin of life is maybe life originated on Earth around these deep sea vents in an otherwise inhospitable environment. And that's it. And the guy with the hook is here. So. See you next time. Yeah, you're welcome.